Hello students, the topic is bandwidth utilization. Whenever we establish a connection, the network provides us some signal strength or the bandwidth. So under the bandwidth utilization, we will discuss two things. Number one is multiplexing and the second one is spreading. So first of all, let's discuss what actually bandwidth utilization is. So basically bandwidth utilization is the use of the available bandwidth to achieve specific goals. Efficiency in the bandwidth utilization can be achieved by multiplexing, privacy and anti-jamming can be achieved by spreading. So in order to achieve the efficiency we make use of the multiplexing, and in order to achieve the privacy or the anti-jamming or to control the traffic on the network we make use of the spreading, right? And both these are possible because of the bandwidth utilization. So these two are the specific goals we want to achieve through bandwidth utilization. So now let's discuss about the multiplexing. Multiplexing basically is the technique we use for the transmission of multiple signals along a single transmission link, right? So we are having a multiple signals, but the transmission, that is the link, we should say, that is transmitting it, that is single. So under the multiplexing, we will discuss these topics: frequency division multiplexing, wavelength division multiplexing, synchronous time division multiplexing, and statistical time division multiplexing. Let's discuss them one by one. So first, this is an example that we are having some input lines from here. Here we are having the mux and here we are having the demux, right? So from here some signals are going through, the multiple signals are going through the one link, right? So this mux is generating a single link, and then this demux is again spreading it into the multiple lines, right? So this is how multiplexing works. Now we will discuss the categories of the multiplexing. So here we will make use of the analog and digital multiplexing. So in analog multiplexing we discuss two categories, that is frequency division multiplexing and wavelength division multiplexing. While in digital multiplexing we make use of the time division multiplexing. We will discuss them in detail later. So first one is frequency division multiplexing. So here you can see that different channels are created for the transmission of the different lines, or we can say the input, and they pass through the mux. Here the channels are created and then they pass to the demux and they are delivered to the destination. So this is frequency division multiplexing. So this is the FDM, frequency division multiplexing, is an analog multiplexing technique that combines analog signal, right? So as the frequency division multiplexing is the analog technique of the multiplexing, so it will combine the analog signal into the one and then transmit them to the destination node. So now this is a detailed explanation or representation of the FDM process. Here you can see that we are having some baseband analog signals, right? And then they pass through the modulator and the carrier waves are generated, and then they are some wrapped up into the some sort of the envelope. Same is the case with the second signal, same is the case with the third signal, and then here they are combined into the one signal, one link is generated for them. Then next they are passed through the filter, then they are filtered out the waves. So here from the first, from the envelope, the carrier wave comes out, and here the demodulator will again convert them into the individual baseband analog signals. So this is how FDM multiplexing technique is used. This was an example to explain that. So the next you can see that is the same example, that here the wave first passed through the modulator. There is, you can see that is the some range of the baseband signal, that is 4, and then again, so we are having 3 signals, so 4 into 3, that makes a sum of 12. So the range of the link, this signal will be 12. You can take it any range, that can be 1 to 12, 12 to 24. So here we have taken the 20 to 32. So there is a difference of 12. right? So this is the same example we discussed earlier. Now we are having an example over here that we are having 5 channels each with 100 Hz bandwidth are to be multiplexed together, right? So we are having 5 signals of 100 kilohertz bandwidth each, and the task is to multiplex them. What is the minimum bandwidth of link if there is a need for a guard band of 10 Hz between the channels to prevent interference, right? So what is a guard band? Guard band basically we use to avoid the interference or any noise disturbance. So as you know that we are having 5 channels, each is the bandwidth 100 kilohertz. So 5 multiply 100, this is the calculation. Now for the guard band signals, so let's see that how many connections are there between the channels, right? So there be the 4 differences between the 5 channels. So a guard band is of the strength or the bandwidth 10 kilohertz. So we are using, if we are using 4 guard bands, so multiplied with that strength, so we will get the sum here 540 kilohertz, right? So this is how we can calculate the bandwidth. Here you can see that we were having the 5 signals, 5, let's go back, we were having the 5 channels of 100 kilohertz bandwidth each, 1 2 3 4 5. So guard band is used in between 2 channels, one is here, one is here, one here, and one here. So we were using 4 guard bands of 10 kilohertz each. So 4 into 10, 40 kilohertz. So we are using guard bands, 4 guard bands of 40 kilohertz bandwidth. So we will, and the channel bandwidth is equal to 500. So 500 plus 40 is equal to 540 kilohertz. So this is how we made the calculations, right? Now there is another example that of the FDM, that we are having different digital signals, right? So this is the quadratic amplitude modulation. If you remember, we discussed in how we were converting the digital signals into the analog signal. So here there is a conversion from the digital signal to the analog signal, and then they are passing through the FDM where they are collected, or we can say assembled into the one single channel, right? So this is another example of frequency division modulation. Now there is an analog hierarchy. You can see that here we are having some 12 voice channels of 4 kilohertz each. They are passed through the frequency division modulation, and then there is a group of 12 voice channels 48 kilohertz. Then same two, we are having 60 voice channels of 240 kilohertz, then 600 channels, then 3600 channels. So this is just a hierarchy in order to show the analog signals FDM process, right? So now we are coming again to the wavelength division multiplexing. So in it is very quite understandable from the wavelength division multiplexing, from its name, that we will be dealing with the wavelengths over here. So previously we were dealing with the bandwidth of the signals. Here we will be dealing with the wavelengths of the signals, right, or the waves. So here we are having 3 wavelengths, and when they pass through the wavelength division multiplexing process, so they are sum up into the signal link, and then again they pass through the demultiplexer, and here they are reassembled, right? So from multiple wavelengths, single wavelength, and again after process multiple wavelengths. So this is how wavelength division multiplexing works. WDM is an analog multiplexing technique to combine optical signals, right? So this is basically dealing with the optical signals, the wavelength division multiplexing, right? Here is another example where we are having some prisms and in between the link is of the fiber optic cable, the channels of the fiber optic cable. So on the one side you are seeing the multiplexer, on the other side you can see the demultiplexer. So here we are having different wavelengths of some optical signals, and they are assembled into a single optical signal, and then after passing through the demultiplexer we are again reassembled, or is splitted into the individual wavelengths. So this was an example how we make use of the prisms in the wavelength division multiplexing and demultiplexing. The next is TDM, time division multiplexing. So here you can see that we are having some different ranges of the times, and this after passing to the mux, they are divided randomly, or we can say that they are interleaved fashion divided, and then after they pass to the demux demultiplexer, and they are again splitted into the individual times. So this is how the time division is splitted, right? So TDM is a digital multiplexing technique for combining the several low rate channels into one high rate channels. See, here we are having the signals of very low rates. That is, 1 is a very low rate, 2 is a low rate, 3 is a low rate, and 4 is also a low rate. So we'll combine all these and we will generate a one link of very high strength. See, we have combined them here. So this is the function of the time division multiplexing, that this is converting the low rate channels into the one high rate ones, right? Now, the synchronous time division multiplexing. So in synchronous time division multiplexing, you can see that we are given some data from different lines. So it will take, in case of the synchronous time division multiplexing, it will take a bit from every channel, we can say, or link, and they will make a one single frame over here. You can see it has taken A1, B1, C1. So, and then after passing to the multiplexer, they have made a frame of one bit from here, one from here, one from here, right? So this is how synchronous time division multiplexing working. In synchronous time division, the data rate of the link is n times faster and the unit duration is n times shorter. So it is working very fast, but the time taken is very low, right? Here you can again see that the low rate signals are combined, or we can say that synchronous TDM, how it is working, that it is taking one bit from every channel and then making a one frame of it that is very fast and with a very minimum time, right? So this is what we were talking about, the interleaved fashion earlier. So this is how they takes the bits in the interleaved fashion and then make one frame, right? So this is again the same case of the synchronized FDM TDM, sorry. Now again is the same case. So this is similar to the previous example. Here you can see that if we are having some empty slots, right, in the channel, maybe we are using some guard bands over here, right? So here you can see that there are no empty slots in the first while taking the first bit, but secondly we are having some empty slots, right? So we will leave while making the frame for it, we will leave that space empty, right? So this is the case of empty slots. If we are having the multi-level multiplexing, right, so we will be doing the multiplexing at the two ends, right? So first we are having multiplexing at this end, and the secondly we are having multiplexing at this end. So this is multi-level multiplexing. So multiple slot multiplexing, this is the same case we were earlier discussed, that we are doing the demultiplexing and then again doing the multiplexing, right? So this is the multiple slot multiplexing. Pulse stuffing. So pulse stuffing is that as we have discussed in the topologies, we were using it is doing the same function as the repeater was doing in the topologies. Say here we are, you can see that we are having two signals of 50 kbps and one signal is 40 kbps. So this, in order to re-strengthen this signal or bandwidth, we are using the pulse stuffing technique. So it is giving us again the strength of 50 kbps, and then we doing the multiplexing on it, so we get a sum of 150 kbps. So this is about the pulse multiplexing, right? The next it's the framing bit. So we have already discussed that how the frames are made in the interleaved fashion. So the TDM was doing this and making the frames from every node of the every channel or link, right? So this was all about the multiplexing.